Hello, and welcome to the 2024 Wolfram Tech Conference and my talk, Quantum Chemistry Tools in the Wolfram Language. Let's see, I'm pre-recording this talk because, my children's school has a fall break, and that overlaps with the tech conference, and so that's our one chance to take this vacation, and we are doing it. So I do hope that you enjoy the talk. Wish I was there to answer questions. Let's see. So this is the abstract slide. The abstract is, it's available. I just want to give a little bit of background about myself. I got my PhD in 2010. I studied electronic structure. I studied simulating time-dependent optical and X-ray spectroscopy. Um, and this type of spectroscopy really involves, shining light on molecules and then seeing having that molecule absorb some energy from the photon and transfer the electron or the nuclei to a higher energy state. And in order to simulate such things, we generally use electronic structure software. And so in 2016, I came to work for Wolfram Research. Have been working to develop new capabilities for Wolfram Alpha and the Wolfram language ever since. In version 12, we introduced a molecule, a symbolic object for representing molecular systems. And since then, we've been adding new functionality to use and analyze the molecule. And and so this is another extension of that work and something that I've been looking forward to doing for a very long time. So first, let's ask, what does electronic structure software do? Um, Essentially, it needs to solve the Schrodinger equation, right? For this system which is a collection of atoms and atoms and um, yeah, that's all it really is. You've got nuclei and electrons, and we like to think of a concept of bonds, a covalent bond between the atoms, right? So let's just look at a random molecule here, and so yeah. If we look at that guy, we've got all these atoms, which we like to represent as spheres, and we color code them so that we know, oh, well, that guy's red, he's an oxygen atom. These gray ones are carbon, the white ones are hydrogen. And we draw these tubes in between them to represent that there's a bond there. And what we really mean is that there's a greater electron density between those two atoms. And so therefore they are kind of the two nuclei are pulled in towards each other. There's a strength drawing them together. And what that really means is that if you solve the Schrodinger equation for the entire system, then you end up with wave functions for the electrons. And when you look at the electron density, the sum of all those wave functions squared, then you'll find that there actually is a density in between the nuclei, and that's what holds everything together, right? And so electronic structure software is what we use to simulate that. So it's a tough job in general, like a multi-electron system is difficult. And so oftentimes what we do is we solve things iteratively using 1 and 2 electron integrals, right? To try and figure out the wave function for these guys. We often make approximations to the orbitals by using Gaussian type orbitals because these are much easier to integrate over than Slater type orbitals. Um, we then we use certain basis sets that expand the wave function in terms of GTOs and polarizable functions, double and triple zeta functions. These basis sets can get pretty interesting and more complicated, but they can get more and more accurate results. Let's see. So we use these things, as I said, we use them to simulate spectra. Um, that's a useful tool for this, or a useful application. There are lots of different methods. So you've got your basis set, you've got your orbitals, and then how do you actually take those things and solve the problems? Well, you can go Hartree Fock, you can use density functional theory, you can use complete active space models. And so there's a lot of different methods. And yeah, So there's a wide variety of software to do this, and uh, uh, let's see, a large different array of different types of methods. So how do you traditionally run electronic software? Electronic structure software. How do you compute these orbitals? How do you solve the Schrödinger equation? Well, traditionally it's from the command line, not using a graphical user interface. So what you do is you prepare an input text file with the molecular geometry and a set of keywords that describe the job and the parameters. Um, then generally those results are then piped either to a plain text file or a binary file that can be read by some other software. Um, so what I've always found is that this requires you to know the input keywords and the syntax, and it requires parsing the output files to get the information you need. And as I mentioned earlier, I did this during graduate school, and so that's kind of what I was doing all the time was I would write a script at the time, in Mathematica, I would write the script to generate a bunch of input files, and then I would run them on the cluster, and then I would get the output files, and I would write another script in Mathematica to go in and get all the information I needed. But let's just look at kind of how these input files work, right? So here, so this is NWChem, and so you have to know basically that let's see. So in this particular case, you specify that you're putting the coordinates in Bohr radii. You have to specify what the basis set in this particular format. And then, yeah, and so that's the input file. And then once you run it, you get an output file kind of like this, which has a bunch of a lot of information, right? You can you scroll through, you parse, you find all the for every time it iterates, right? I said it's an iterative process, and so it'll output the information at every step, and so those things can be difficult to parse, but if you know how to, it's a whole bunch of information. Just quickly, here's what a Gaussian input file looks like. Same kind of information, different format, right? And you really have to know what these keywords, right? So this is we're doing a geometry optimization. We want vibrational information. Let's see, the geometry equals. I gotta say, I don't really have all of these memorized, and that was kind of my problem back in the day. I did not. I had to you have to look up what all of these little words mean and get the right incantation to get it to work properly. But there's lots of help available, and it's a doable problem. But to be honest, this was always a barrier to me, uh, the the way that these things were set up, right? Um, and then again, I'll just show this is what the output file looks like. You need to learn how to parse this. And so, okay, so parsing those output files, that's something we can look at first, right? So we have this function called import computational chemistry data. It's in the chemistry functions paclet, right? So that's do paclet install Wolfram chemistry chemistry functions, and then once you have that, you then do needs Wolfram chemistry. You change the slash to a backtick, and add a backtick here, and boom, you've suddenly got import computational chemistry data. So this is a function that tries to parse all of those different output files. It uses the cclib Python library. This is an open source library that has a lot of contributors, and so the point here is that it has a consistent data structure to represent the output for the computational chemistry from all of these different files or programs. Sorry. And then it tries to search out the relevant information and put them in a nice structure. And so what we can do is we can once you've loaded the paclet, you can look at let's see, this one is divinyl benzene, a geometry optimization using Hartree Fock, and you can try and import it and see all the different information that is available, right? And so let's actually look at what it looks like. When you import it all, you get atomic orbital names, the overlap matrix, partial charges, the Gaussian basis, all of this information. You can then take that and make a vibrational, an infrared spectrum from it. And yeah. So this function actually came out last year. And so we've been able to import computational chemistry data, but we haven't actually been able to run one of these computational chemistry jobs, right? And so we can do that now with the Wolfram language using a free Python program called PySCF, and it uses the external evaluate functionality. And so again, it does involve an unfamiliar syntax. I say unfamiliar because myself, I speak Wolfram language. When I read Python, I have to translate it in my head, so to speak. But you can see how this works. You create a mole object, an empty mole object, then you populate its atoms, you specify the basis, the symmetry, then you create this mean field object it's a method, in this case, restricted Hartree Fock. So again, you have to know what these words already mean. And then you call the kernel function, and that actually runs it. And so let's show what the output from that is, right? So it's actually pretty verbose. It prints all this stuff out, and then in the end, it returns you the energy. It tells you that it's converged, the self-consistent field converged to this number, and we actually know that it's in electron volts. And so what we can do is we can then, let's see, what I'm trying to say is that rather than do that using Python in your notebook, we can write a whole set of functions that call Python and use a syntax that's more familiar to a Wolfram language user. And this is all built around the external evaluate functionality, something that's really gotten a lot more robust in versions 14.1 and especially in version 14.2 with the introduction of external object, external function. There's a lot of interesting stuff that can be done. So in this case, if we wanted to just look at water and get the ground state energy, we call electronic. So this is the function that I'm writing right now, and it will be in the next version of the chemistry functions paclet that we talked about. So we call it electronic structure. We give it the first argument, molecule of water. We tell it the job type that we want, and then we give it the basis set. And so that is going to run, and it's going to return something called an electronic structure result. And we ask that for a sub-value of it, and that's the energy. And it comes out as a nice quantity object that tells you what its units are, and it's a computable and fits into everything here in the Wolfram language. So now, let's see. So what are the goals then of this project, right? And so what we want to do is provide a consistent method for setting up and running electronic structure calculations with descriptive job titles, parameter names, rather than the shortened keywords that can confuse new users. Of course, the shortened keywords should still work as aliases for those people who've been running computational chemistry jobs for years and have no problem with the words just writing RHF or DFT or TD or CI for configuration interaction. So what we like to be able to do here is compute ground state electronic wave functions, excited state, transition dipoles, visualize molecular orbitals, do geometry optimization, vibrational analysis. These are all the wish list. This is a work in progress, and we've got a good chunk of this working already. Eventually, I'd like it to work with other backends in addition to PySCF, like Gaussian or NWChem or Psi4, and use the same set of functions as the front end, and all of the writing the input files to call those, that should be handled in the background. And then after that, we'd like to provide additional functions for analyzing those electronic structure results, right? Like simulating optical and infrared spectroscopy, animating the vibrational modes, computing multidimensional potential energy surfaces from which you could analyze nuclear dynamics. Right. So let's look at this function that I've written and kind of been working around with. It's definitely a work in progress. It's experimental, and it might the syntax might change as we move forward and try and find out what exactly works and what doesn't work on it. So the first object, as I said, is a molecule, or the first argument. We should be able to extend this to work on biomolecule, but obviously working on a system with hundreds or thousands of atoms can be taxing on your hardware. And so there are limits to what you can do. Let's see, the job type. Currently, we support ground state energy, excited state energy, and geometry optimization. Others will be added to that, surely. And then the parameters. This is where this is an association specifying the model chemistry, right? So model chemistry means, for example, like unrestricted Hartree Fock with a 6-31G basis set, something like that. Those are all provided here in the associations parameter, the parameters association. And then calculation parameters like the maximum memory, the file that you'd like to dump intermediate results to, stuff like that. So what does it return? It returns an electronic structure result. It's this blob here when I ran it, right? And so it's got sub-values, or sometimes we think of them as properties, is what they were previously called. So it's got sub-values from which you can get the molecular orbital, the orbital occupation, dipole moment, let's see, rotational constants. It stores a copy of the input molecule, and it has a copy of the output molecule in the case where things change. And then it can be used for further computation. So you can take this electronic structure result object and pass it into electronic structure plot 3D. So you've already computed all the orbitals, and you just need to you want to plot them. So this has all the information you need. And this is something that will be introduced going forward, you can use it. So first you run a job at a lower level of theory, right? So using restricted Hartree Fock and maybe a smaller basis set. And then you want to improve that calculation so you can use the initial density matrix as a guess for the higher level computation. So yeah, so these are the properties that it has, right? It also stores some of the meta information, which basically says the package used to run the software, the memory available, the CPUs, the symmetry. Yeah. So you can then, for example, take the molecular orbital energies and plot them. You can look at the actual Gaussian orbital basis. Yeah. So let's move it along here. Right, okay, so let's compute a ground state potential energy curve. So since version 12, the Wolfram language has had a couple of built-in molecular force fields, the MMFF and the UFF. So these are empirical force fields, right? So they provide a classical approximation for these molecular interactions. They're great for large systems, out of the range of the wave function-based methods, very fast. But they have their limitations. So here I'm looking at H2, right, and a hydrogen molecule. Well, the MMFF is not parameterized for that, so we can't use the MMFF for H2, which is perfectly fine because the MMFF was made to study interactions of large molecules, right, and for use in drug design. The first M here stands for Merck, and you really don't need to model molecular hydrogen using MMFF. But the UFF is universal, so it can be used for anything. If the MMFF were parameterized for H2, you would see a similar thing here. So what I'm doing is getting the stretch energy for this one-dimensional system. I'm taking my molecule, which is just two hydrogen atoms with a single bond, and I'm locking the first atom at the origin and setting the second atom some distance d away. And I'm finding the UFF energy going from really close together out to a distance of 3 angstroms. And then I do a list line plot, and you see here, well, sure, it has a nice low energy spot here about where it's supposed to be, right? I mean, we should have, what do we want there? We want it to be like 0.74, I believe is the right answer for the bond length. And you've got a nice minimum there. So near that minimum, you're going to get a decent amount of, it's going to reasonably approximate the actual potential. But when you stretch that H2 out to 2.5 angstroms or 3 angstroms, the energy just keeps getting higher and higher because this is just a rubber band. That's all that we've got going into it. So instead, we can do a ground state energy calculation using restricted Hartree or unrestricted Hartree Fock and a 6-31G basis set. We can grab the energy from that and then plot that from 0.2 angstroms all the way out to 5 angstroms. And we see something that looks a lot more reasonable. So again, you've got a minimum energy spot here. When the atoms get close together, the energy rises very much, which we missed in this force field. And then at long distances, it kind of levels off, meaning if you have your 2 hydrogen atoms 5 angstroms away from each other, there is no bond. So that here we're accurately capturing that physics. And then let's see, just for fun, we can compare that to the same thing we get when we run a density functional theory calculation. And we see here, so that's in orange, whereas the Hartree Fock is in blue. So you can see some differences in the approximations. And to be honest, that is a testable thing, right? So you could compute the vibrational eigenvectors here and find the transition energies and compare that to an infrared spectrum, and boom, you would see which is more accurate for this. You can also then use this function, which I'll show in a coming slide, electronic structure plot 3D, to kind of look at the electronic density as these two atoms approach each other, starting at 5 angstroms apart and then coming closer to 0.5 angstroms. And then you see initially there's no density between them, and then boom, we have a bond forming. I should work on this movie a little bit better. It should have a consistent size and viewpoint, but let's delete that so that our notebook isn't terribly bloated. All right. So visualizing molecular orbitals, right? So here we go. The function here is electronic structure plot 3D. We can give it just a molecule as a first argument, in which case it's going to call the electronic structure function in the background. And so here we look at the highest occupied and lowest unoccupied molecular orbitals for water. And this just uses actually the default basis set, which is pretty small, to be honest. It's called STO3G. And so we can run the same calculation using a larger basis set. And we can see that the HOMO, highest occupied molecular orbital, is essentially unchanged, whereas the LUMO is definitely different in character. And again, this is going to be something that is testable. You can compute the transition dipole, the energy difference between these two orbitals, and that should tell you something about the optical spectrum. You can plot instead of HOMO or LUMO for the second argument, you can give the word density and plot the electronic density. Let's look at a more involved example here. This is a metacyclophane. This molecule was recommended to me by Bob Nakbar for a different example, but I thought it'd be neat to look at the orbitals here. We have two benzene rings held with let's see, the word meta comes from the fact that these bridges are meta to each other, right? So they're 2 bonds apart. And so let's look at that. So in this case, running the electronic structure job on it takes a good amount of time, and it took about 75 seconds on my machine. So we run it once, Res equals electronic structure of M, the ground state energy, and we'll give it an even bigger basis set here, right? Correlation consistent, polarization, um, split, double split zeta. Yeah, I'm not going to pretend to have actually read the paper behind that. But I do know that these are good. Let's see. So let's look at the highest occupied molecular orbital for this metacyclophane, and it's good. You see some pi orbitals here on the benzene rings, and then some orbitals on the bridging atoms. And now when we look at, so we can also say HOMO -1, and so that is the second on. Let's see, the second highest occupied molecular orbital. And then we can also look at the LUMO, right? The lowest unoccupied molecular orbital. And here we actually see the wave function has a lot of activity going on between the two benzene rings. And that's got to have some impact on the spectrum for this molecule. And again, you can you can say LUMO +1 to get the next one, LUMO +2. We can even go so far as plot an arbitrary orbital. Now this is 300, and so it's very high above the highest occupied molecular orbital. And so in that case, this might not necessarily be all that physical, to be honest, right? When you get to the top of the close to the top of the expansion, some of them, yeah, they get pretty wild. Or you can look at an occupied molecular orbital, number 30. Right, and so then this is my final slide. I'm out of time, it looks like. So look for these functions in the Wolfram chemistry function paclet when Wolfram version 14.2 is released, and this will be in the Wolfram Language Paclet repository. Thank you very much for your time, and enjoy the rest of the conference.